This is the video for 7-6, and we are talking about exponential functions. An exponential function is an equation of the form y equals a times b to the x power, and b must be a positive number. So example number 1, identifying the difference between a linear and an exponential function. The first example is an example of an exponential function. So how do I know that this is not a linear function? Well, my slope or my rate of change is not consistent. Every time x goes up by 1, y is decreasing by a faster and faster rate each time. So this is an exponential function. The next example says y equals 3 times x. That is an example of a linear function. Your slope or your rate of change on this graph will be consistent. So whenever you have y equals mx plus b or y equals kx, as in this situation, this is a direct variation equation, remember from last semester, so this is a linear function. So go ahead and hit pause and work out the two on your own problems and identify which one is a linear function and which one is exponential. This is a linear function because my slope or rate of change is consistent. Every time x goes up by 1, y is going up by 2. And this is an exponential function because it is in the form of y equals a times b to the x power. Example number 2, writing and evaluating an exponential function. There are 30 beetles located in a certain area. If there are no natural predators, this particular beetle population doubles each week. What equation represents the beetle population and how many beetles will there be after 56 days? Okay, so let's think about what happens after week 1. After week 1, our beetle population doubled, and so now we have 60 beetles. What happened after week 2? Our beetle population doubled again, and so now we have 120 beetles. What happened? After week 2, we took our initial beetle population and we doubled it twice. And so now what happened after week 3? Well, now we took at the end of week 3 or after week 3, we've taken our initial beetle population and now we've doubled it 3 times. So now we have 240 beetles. And that's how we can write that situation. We doubled our initial beetle population 3 times. So what are we doing, and what's the equation that represents the growth in the beetle population? What am I doing? I'm doubling my population every week. So I can say y, which is the total number of beetles, equals 30 times 2 raised to the x power when x equals your number of weeks, because I'm doubling my beetle population every week. Well, now let's answer the question. How many beetles will there be after 56 days? 56 days is 8 weeks, so we will have a total of 7,680 beetles. Now go ahead and hit pause and work out the next on your own problem. And here's the answer. What am I doing to this initial population of rabbits? My initial population is 20, and every 6 months, I'm tripling the population. Example number 3, graphing an exponential function. So I want you to start by graphing these by hand. It says identify the y-intercept, the domain, the range, and the asymptote. An asymptote is a line that a curve approaches as it heads towards infinity. Pause the video and write that down. The definition of an asymptote. It's a line that a curve approaches as it heads towards infinity. So how did I develop the graph for this exponential function? Well, first of all, I know what my y-intercept is just by looking at it. The A is always going to be your y-intercept because it is the value of y when x is 0. When x is 0, this is going to be 1. And so then y would be 3. The y-intercept here is going to be at the coordinate point 0, 3. The y-intercept is going to be the value of y when x is 0. So you can see when x is 0, y equals 3 because 2 to the 0 power is going to be 1. So that A value is going to be your initial. It's going to be the y-intercept. So I found my y-intercept just by looking at it, and then I just grabbed some other coordinate points. I created values for x, and I plugged them into the equation, and I determined their corresponding value for y. When x is 1, y is 6. When x is 2, y is 12. When x is negative 1, y is 3 over 2. When x is negative 2, y is 3/4. And pause the video and make sure that you understand how I'm doing this and where I'm getting these numbers from. I worked out this one for you so you can see what I did. When x is negative 2, y is 3 over 4 because 3 times 2 raised to the negative second power is the same thing as saying 3 over 4 or 3 over 2 squared. Because remember, in order of operations, you take care of the exponents first. So then I went ahead and I graphed those points, and I can see my asymptote is at y equals 0 because the line is approaching y equals 0, but it will never reach y equals 0. And you can keep creating negative values for x, and you can keep solving for y, and you will see this line will keep getting closer and closer to 0, but it will never cross over. The fractions will just keep getting smaller and smaller. For example, if x is negative 3, this becomes 3 over 8. When x is negative 4, this becomes 3 over 2 to the 4th power. And the fractions keep getting smaller and smaller, but your y values will never be negative. It will never cross over, or it will never reach y equals 0. So my asymptote is y equals 0. Well, what is the domain and what is the range? The domain, remember, are all of your x values. So in this situation, your domain will eventually be all real numbers, because remember, this graph is going to keep going out this way towards infinity and keep going out this way towards infinity. So this graph will eventually cover all possible x coordinate points. So the domain is going to be all real numbers. However, your range, which are your possible values for y, your range is going to be greater than 0. Y must be greater than 0. Because remember, this will keep approaching y equals 0, but it will never reach y equals 0. So your asymptote is y equals 0. This line will keep approaching y equals 0, but it will never reach y equals 0, and it will certainly never cross over y equals 0. And you can prove that by just creating more and more negative values for x, and you will just see all that will do is just give us smaller and smaller fractions. The domain are going to be all real numbers. Remember from last semester, that's how you write all real numbers. Your range, your y values must be greater than 0. And remember again from last semester, that's how you write in interval notation y is greater than 0. Okay, so go ahead and hit pause and work out the on your own problems that are on the next page. Here's the answer to the first on your own problem. You can see the graph. My y-intercept, I can look at this and I can see that my y-intercept, or my initial value in this situation here, is going to be 0.5. 0, 0.5 is the y-intercept. My asymptote is y equals 0. What does that mean? It means this graph is going to be coming closer and closer and closer and closer to y equals 0, but it will never cross over. You can see as these x values get more and more negative, all that's going to happen is our fraction is going to get smaller and smaller and smaller. So this will keep getting closer and closer and closer towards y equals 0, towards infinity, but it will never reach y equals 0. So my possible x values, or my domain, are going to be all real numbers. However, my range, or my possible y values, all of my possible y values in this situation must be greater than 0. My range is y is greater than 0. And that's, remember how we write, y is greater than 0. And here's the graph for the next one. Notice the numbers are going to be the same, they're just going to be negative, because it's negative 1/2 times 3 to the x power. So how does this change my situation? Well, my asymptote is still y equals 0. This is coming closer and closer and closer towards y equals 0, but it will never reach it. My domain, or my possible x values, are still going to be all real numbers. However, my range, or my possible y values, here y is going to be less than 0. My possible values for y must be less than 0. And this is how we write that. And finally, example number 4, solving one variable equations. So this is asking you, for what value of x will these equations be equal to each other? In other words, if I were to graph this and if I were to graph this, where would they intersect, and what is the x value? What is the x coordinate point at their point of intersection? So now this is what I want you to do. I want you to go to this website. I want you to use this website, and I want you to graph. This is called Desmos, www.desmos.com. And I want you to graph this equation, or this function, and then I want you to graph this linear function. I want you to graph this exponential function, and then on the same coordinate plane, I want you to graph this linear function. And I want you to determine where do they intersect and what is the x coordinate point at which they intersect. So pause the video and do that right now. Okay, so I went to desmos.com, and you can see I typed in both equations and it gave me a graph, so I can see what this looks like on a colored graph. And I want to encourage you when you're doing your homework and when you're graphing all of these exponential functions, go to Desmos.com, type in the equation and see what it looks like on a colored graph. And so now I just see, well, what is their point of intersection? What is the x-coordinate where they intersect? So they intersect at approximately negative 3.9. It says negative 3.863 and 1.445. So that's how I want you to solve those problems. Go ahead and hit pause and work out the next on your own problem and practice graphing it on Desmos. And here you can see they only intersect at one point, and the x-coordinate point where they intersect is at negative 0.452.